Okay, so let's look at some more examples of these indefinite integrals. And again, how do I know they're indefinite integrals? There are no bounds, right? So there's nothing here that we're trying to measure area under. We have to interpret this symbol as saying, okay, it's kind of like an accumulation function. We're just missing the bounds. So all it's really looking for is an antiderivative, right? It's looking for a function a function whose derivative is sitting right here. So can you think of a function whose derivative is 6x squared? Like another way to think about this is I could say the derivative of something is equal to 6x squared. What would you have to have started with? Well, you can think about it should be cubic, and you can think about, like how do we deal with this coefficient of a 6? Because if it was cubic, the 3 would have come down. So if you would have, like, let's say, like 2x cubed, right? Think about that. 3 times 2 is 6, and you would have decreased the x1 by 1. So you get 6x squared. But the thing is that maybe it was 2x cubed plus 1, or maybe it was 2x cubed plus 11, or maybe it was 2x cubed plus 11 over 3. Like there's an infinite number of coefficients. So we have to recognize that there could have been a constant there. So we just say it's 2x cubed plus c. This is the family of functions. As long as that's a constant, any one of those functions' derivative would be 6x squared. Okay. Same thing here. Even if there's two pieces to that function, look at them kind of separately and think, okay, the derivative of something was equal to x cubed minus 2x. What would you have to have started with? Again, this is an antiderivative. So, go backwards. And you think, okay, well, to get cubic, you would have had to start with a fourth power. And there is no coefficient there. You want those fours to cancel. Like the 4 would have come down, canceled, great. And then minus 2x could have been minus x squared, right? 2 times x would have been its derivative. And then it could be any constant value that you choose. There we go. So it's just an antiderivative. And again, maybe I'll even talk about this. Antiderivative. Derivative. There it is. Okay. All right. Now, of course, we have to do trig, right? So again, thinking about this right here. So whose function's derivative is cosine? We're going backwards, right? So the derivative, again, thinking about this, the derivative of something was equal to cosine. What did you have to have started with? The sine function. Sine function plus some constant. And then same thing here. What would you have had to have started with? Again, the derivative of something is sine. Well, since that's a positive sign, we would have started with negative cosine plus some constant. Okay, so again, focus on when you see this symbol. This is the antiderivative symbol. Right? There are no bounds. So we're not measuring area under a curve. We want to think about that as an accumulation function that just doesn't have, that doesn't have any boundaries. So we're just looking for just like the generalized function. Where would you have started? And again, there's some mystery here with like somehow area is related here too, just not yet. Okay. Good. One more trig, secant tangent. So you think about whose derivative is equal to secant theta tangent theta. And you don't have to always draw this out, but we should be thinking about this because it helps us kind of get through that process. The derivative of secant is secant tangent. So we just say it's like secant theta plus some constant because we don't know what that constant is because when you take its derivative, it goes away. Now, we can get things a little bit more complicated in a way. A square root, just have to think creatively that this is really just a half power. So this is 2t to the half power. And this one here, we could think of that as 2y to the negative 10 power. And each of these, like if you're undoing the derivative and it's a power, well, derivatives take powers down. You multiply the power down, right? So an antiderivative would multiply the power up. I mean, think about what we just did here. Like go back up to this example, x cubed, right? So if I just had the antiderivative of x cubed, you're just going to do the derivative backwards. So instead of bringing the 3 down as a multiplication and decreasing it by 1, you're going to increase it by 1 and then divide it, right? That's the exact opposite. And then you add the constant. So the power rule is that you bump it up a power and divide by that power. The same thing would have happened here with 6x squared. The antiderivative of 6x squared is you bump up that power, 6x cubed, and then you divide by that power. And if you think about it from that perspective, if we think about it from that perspective, like these would always match, right? That gave us our simplified 2x cubed, so it works. So that power rule applies here. So we could bump that up a power and write that as 2t to the 3/2 power. That's one power higher, right? That's one whole number higher, and then divide by that 3/2 plus our constant. And normally we wouldn't leave it like this. We'd multiply by its reciprocal. So we get 4/3 t to the 3/2 plus c. So we get that. Okay. And then here, 2y to the -10. So that could be thought of as 2y, bump it up a power. So -9 over -9 plus c. So you're just increasing it by 1 and then dividing it out by that value. And then you could leave it like that, or you might see it as 2, or I should say -2 over 9y to the 9th plus c. Now, do not forget that constant. That constant is so important, and in fact, it's so important that you lose points on the AP exam if you forget it. Okay? And so then the last example here, the integral of 4, at least like the last one in this box here, the integral of 4 dt. Okay, so we can think about this. That would just be that's the 0 power, so you bump it up, that's like 1. But the thing you have to be careful of is the variable is t. So it's 4t plus c. Because this variable, this dt, tells you what the derivative was with respect to. So it's 4t plus c. If you had 4x plus c, it's the right family of functions, just the wrong variable. And then power rule works for fractional exponents. So 2y, so raise this up a power. So that'd be 9/5 divided by 9/5 minus 7y to the 5/2 divided by 5/2 plus c. And then we could flip that around so that the 5 comes up to the top. So that's 10/9 y to the 9/5 minus 14/5 y to the 5/2 plus c. Okay, so again, thinking about this antiderivative, finding a function whose derivative is equal to what is inside that indefinite integral symbol is exactly what we should be looking at for that particular problem.